Welcome back to the Deep Dive. Today we're plunging into a topic that feels like it's fundamentally reshaping not just AI, but our very interaction with technology. We're talking about artificial intelligence moving beyond the screen and right into our physical world. Our source for this is a really fascinating article from datapro.news. It's titled "How Large Behavior Models Are Rewriting Data Engineering Pipelines." Samuel Williams wrote it, published back on September 3rd, 2025. And this piece, it really lays out how generative AI isn't just like a digital assistant anymore churning out text. It's actually stepping into our physical reality, driven by something called Large Behaviour Models, or LBMs. So our mission today is to unpack exactly how these LBMs are causing a complete rewiring, that's a term they use, of data engineering workflows, tools, even the mindset. We're moving from a world focused purely on language to one driven by behavior and embodiment. Okay, let's unpack this.
What's fascinating here is exactly that core shift you've highlighted. I mean, if the early days of AI were primarily about understanding and generating language, text stuff that happens digitally, the LBM era is truly about behavior and embodiment. We're talking about machines that don't just reason or process information internally. They act. They act in the physical world, and they learn and adapt through that physical interaction.
Right.
And that, well, it has immediate and pretty dramatic implications for how we design and manage data pipelines, moving away from the traditional, often static batch processing stuff we've known for so long.
That's such a crucial distinction because we all know large language models, LLMs, your GPT-4, Gemini, Claude, they absolutely revolutionize language tasks. Writing, summarizing, even drafting code brilliantly. And then you have the small language models, the SLMs, kind of the nimble, efficient versions for specific jobs. But their fundamental limitation, as you said, they live purely in a world of words. An LLM can describe how to tie a really complex knot, but it can't physically do it. That gap, that difference between describing and doing.
Yeah.
That's what LBMs are meant to bridge, isn't it?
Precisely. LBMs aren't just reading text or parsing tokens in some digital void. They learn from action. Think of it like a continuous feedback loop. They watch demonstrations, they analyze these nonstop sensor streams from the physical world, they simulate new behaviors, and then they act. And crucially, they fuse that language understanding with physical senses. Proprioception, the sense of your body's position in space vision, obviously, and haptics, the sense of touch and force.
Proprioception, right? That sense of where your limbs are.
Exactly. And the analogy here is really quite vivid. Imagine a toddler learning to ride a bike. They learn by trial and error, right? By wobbling, falling, trying again. We call that experience. Well, for machines, it translates into what the article calls real-time data flywheels. These are constant, rapid cycles. Collect data, act, sense the world's response, you refine the behavior.
A flywheel, constantly spinning.
Constantly spinning. And this isn't just some interesting academic idea anymore. It's crashing headlong into the very practical world of data engineering. It demands a fundamental rethink of how things are done.
A toddler learning to ride a bike, that's such a perfect visual. It's messy, right? Full of failures, but eventually, hopefully, mastery.
Oh.
And I guess for data engineers, that mess is exactly what they're now trying to tame. But it sounds like a huge departure from the, let's say, cleaner, more predictable data they might be used to. Which brings us neatly to what the article pretty boldly calls the death of batch. I mean, for decades, data engineers worked with batch pipelines. Static data, clean it, transform it, tokenize, deploy, maybe overnight jobs. That worked fine for LLMs trained on frozen snapshots of text, Wikipedia dumps, scrape forums, whatever.
Yeah.
So how do LBMs just completely shatter this paradigm?
Well, the new reality is that LBMs thrive on continuous streams of data, not static data sets. Just try to imagine the sheer deluge of information coming in. We're talking robotic sensors, for instance, maybe pumping out thousands of measurements per second, data on force, torque, acceleration, proprioception.
Thousands per second.
Yeah. Then you've got camera feeds, LiDAR scans, maybe slower frame rates, but they demand incredibly precise spatial alignment with everything else. You also have human teleoperation inputs, think VR setups, where operators guide robots, and every tiny muscle twitch is captured as multimodal training data.
So you're capturing the human expert's movements directly.
Exactly. And don't forget simulation data. That's synthetic, but it's absolutely crucial for covering those rare edge cases you might not see often in the real world but need the robot to handle safely. Put it all together, and these sources create what the article just nails as a multi-rate, multimodal, asynchronous mess.
A mess, yeah. Sounds about right.
The sheer volume, the variety, all arriving at different speeds, not perfectly synced. Data engineers have to transform this chaos into usable signals. Alignment isn't just, a nice to have, it's survival for the system. The article gives this really vivid example. Teaching Boston Dynamics Atlas robot to carry a tire. If the haptic data, the touch and force info arrives even milliseconds out of step with the camera feed,
You get chaos.
the robot literally won't understand what it's doing. It'll fail. Here's where it gets really interesting. Traditional ETLT, extract, transform, load. It suddenly looks almost quaint,
Quaint. I like that.
Data engineers aren't just building pipelines anymore. They're constructing what researchers are calling data circulatory systems, living, real-time architectures, always pumping, always processing, never static.
Data circulatory systems. That phrase really sticks, being such a clear picture. But, it also sounds like a potential nightmare for someone used to traditional methods. How do you even begin? How do you impose order on that kind of, chaos? What's the very first step in turning that mess into something an LBM can actually learn from?
Well, it certainly redefines the job description. It starts with ingestion, and this is where we move way beyond just pulling from APIs or logs or, dealing with CSV dumps. For LBMs, data ingress now involves things like teleoperation rigs, streaming VR-captured hand and body kinematics straight into the system. It means onboard robot hardware just blasting out multi-kilohertz accelerometer readings, and it includes edge AI chips that process some of that raw sensory input right there before sending maybe just the critical bits up to the cloud.
Processing at the edge.
Which absolutely demands distributed, low-latency, event-driven architectures. The article really emphasizes this. Kafka-like systems or similar streaming platforms, they aren't just useful add-ons, they're the absolute backbone now.
All right, the backbone. So, once that incredible volume of raw, high-frequency, multimodal data is streaming in, what's next? Bringing all those different signals together, different sensors, different rates, that must be a monumental challenge.
Oh, absolutely. Once it's ingested, the real challenge kicks in with transformation. And here, more than maybe ever before, time is everything. Think about it. You've got to merge, say, a 30 frames per second video feed with a 1000 hertz motion signal. That needs real-time temporal alignment just to correct for latency drift between the sensors.
Getting the timing exactly right.
Exactly right. Then you need spatial transformations to map all those signals into consistent coordinate frameworks so the robot knows where everything is relative to itself. And crucially, you need what they call semantic stitching, making sure, for example, that an operator's arm movement is correctly aligned in time and space with what the robot saw at that precise moment. Traditional row and column tables, they just can't handle this complexity anymore, not effectively. So engineers are increasingly turning to things like vector databases and graph-based data stores to somehow unify these incredibly complex structured and unstructured elements.
That's a huge leap from just, cleaning up messy text data. It sounds like you're dealing not just with data integrity, but with the actual meaning and context of physical actions. Which leads us, I guess, to curation. What does curation even mean in this new world? It must be profoundly different from just scrubbing spam off a website forum.
It is profoundly different. And this is where the role of the data engineer gets, kind of existential almost. For LLMs, cleaning meant, removing spam, maybe normalizing token frequencies, simple stuff, relatively speaking. For LBMs, it's existentially harder. The data engineer essentially becomes a quality assessor of behavior itself.
Assessing behavior.
Yeah. You're asking questions like, was that human demonstration smooth and efficient? Or was it kind of sloppy, maybe a jerky move that if the robot learns it could actually be dangerous or just ineffective? Does this specific bit of movement carry enough mutual information? Is it informative enough between the action and the resulting state to be worth the compute budget to train on?
That sounds less like data cleaning and more like
Well,
behavioral psychology.
it's almost like that, like being a behavioral psychologist for data, not just a data cleaner. Teams are already exploring programmatic scoring techniques to classify demonstration data by its learnability or its efficiency. And as the article points out, that's way more subjective and potentially much more dangerous if you get it wrong than just scrubbing swear words from a text corpus.
That's a fascinating and, slightly unnerving shift in responsibility. Okay, so once this incredibly rich, curated behavioral data is ready, how does it actually translate into a robot doing something? How are these models trained and then deployed so they can react in real time in the physical world.
Right. So finally, we get to training and deployment. And this is pushing a new kind of hybrid compute model. The gigantic base model training, the really heavy lifting with hundreds of millions, maybe billions of parameters, that still happens on massive cloud clusters. Think NVIDIA's big DGX boxes, hyperscaler infrastructure, that sort of thing.
Big iron in the cloud.
Exactly. But inference, the actual decision making in the moment, like should the robot turn left now, that has to happen on the device, often within milliseconds.
Right there on the robot.
Right there. This is where edge AI accelerators, things like NVIDIA's Jetson Thor, come into play. These powerful little chips sit inside the robots themselves, running these sophisticated behavioral policies without needing constant chats back to the cloud. But for data engineers, this creates another workflow twist, designing these synced data pipelines that have to seamlessly bridge both the edge and the cloud. Logs, data for retraining, corrections based on real-world performance, all that has to flow back into that global flywheel efficiently without choking the network bandwidth or causing huge latency spikes.
Wow. An incredibly detailed picture you've painted, from the raw sensor input chaos all the way to a robot making decisions in the blink of an eye. Let's maybe try and bring this to life even more. The Atlas Humanoid project that Boston Dynamics and Toyota Research Institute collaboration seems like one of the most vivid examples of all this actually working, right?
Indeed, it is. At its core, the latest Atlas is powered by something like a 450 million parameter diffusion transformer that's handling the whole body control. This type of architecture, diffusion models, it's actually crucial for embodied AI. It allows the model to generate these smooth, complex, highly nuanced actions. It effectively learns to denoise an initial vague intention into a precise sequence of movements.
Denoising an intention. That's a cool way to put it.
Yeah, and what's really revolutionary here is that it's a single behaviorally unified LBM. It's not a patchwork of separate systems, one for walking, another for lifting, another for balancing. It's integrated. The training, as we touched on, relies heavily on these high-fidelity, teleoperated demonstrations, often done in VR. That's combined with a lot of simulation-based reinforcement learning, plus continuous trial and error in the real world. And over months, Atlas starts gaining these skills, flipping furniture, tugging heavy tires, tasks that would have been just an absolute nightmare to try and hand engineer with old-school brittle code.
Things you just couldn't program step by step easily.
Exactly. And for the data engineers working behind the scenes on a project like that, it means building pipelines that capture way more than just, did the task succeed or fail? They need to capture every subtle temporal contour of each movement, the richness and the precision of that continuous multimodal data that is the real fuel driving the quality of these LBMs. It's all about capturing the how, not just the what.
The Atlas project really does showcase breathtaking capabilities.
Mm-hmm.
It feels like science fiction becoming reality. But as you've kind of hinted at, this kind of power, it always seems to come with a darker side, or at least significant risks. The article makes a really strong point that LBMs raise the ethical and technical stakes much higher than purely linguistic AI did. Are these risks fundamentally different, or are they just amplified versions of things we've already worried about with AI?
That's a really important question, and the article highlights, I think, 3 critical areas where the risks are different, or at least felt much more acutely. First, bias can now break bones. That's a stark phrase, but it's true. When an LLM spits out a biased sentence, the worst outcome is maybe reputational harm, misinformation, something like that. Annoying, potentially damaging, but often digital.
Right. Harmful, but maybe not physically.
But when an LBM incorporates biases from its training data into its physical behavior, the stakes immediately escalate to physical harm. Imagine a household robot that subtly misinterprets gestures from people with certain physical characteristics because its training data wasn't diverse enough. Or a robot trained mostly on demos from young athletic people. How does it react? How brittle are its responses when it interacts with, say, an elderly person or someone with a physical impairment?
That's a scary thought.
Or think about a warehouse robot. If its training data mostly showed clear empty aisles, it might develop unsafe, overly aggressive movements when it suddenly encounters unexpected clutter, or worse, a human worker in a real messy environment. The consequences are just far more direct and dangerous.
Okay, so physical bias. What else?
Second, privacy becomes bodily. LBMs, by their very nature, rely on watching and learning from human actions. Those same systems, recording operators tying knots or pouring milk, well, they could just as easily be used to monitor everyday human behavior at scale, in homes, workplaces, public spaces. This raises a huge question. What happens when physical behavioral surveillance becomes the next really fine-grained data set for targeted advertising or insurance risk assessment or worse?
Wow, yeah. It shifts the whole privacy debate from just our online data clicks to our actual physical movements.
Precisely. And third, there's the risk of economic concentration. Training these massive LBMs is extraordinarily expensive. It requires huge compute power, specialized hardware, vast data sets. So, much like we saw with the giant LLMs, this industry risks consolidating around just a handful of hyperscalers and tech giants who can afford it.
The usual suspect.
The usual suspects. This could lead to a kind of tiered AI economy where only these large monoliths really have the resources to develop and deploy embodied AI at scale, potentially leaving startups, smaller companies, even entire countries far behind.
These are really profound considerations. They underscore just how big this shift is. So, okay, for those of us listening, whether you're a data engineer trying to figure this out or just, like me, insanely curious about where this field is heading, what are the key takeaways? What are the strategic recommendations? What does survival or maybe even leadership in this new LBM world actually demand from us?
Right. If we connect this to the bigger picture, what you need to be doing now. The article outlines several pretty clear priorities. First, you absolutely need to re-architect for streaming, mastering event-driven, distributed data systems. It's not optional anymore. Batch processing just isn't the default way to think. The LBM world runs continuously.
Get comfortable with streams. Got it.
Second, build multimodal literacy. You have to get comfortable aligning vision, audio, proprioception, haptics. These aren't exotic edge cases anymore. They are the bread and butter of these new embodied AI pipelines. You need to understand how they fit together.
Speak the language of sensors.
Exactly. Third, think of curation as craft. Treat that behavioral data as incredibly precious. Explore programmatic ways to score its information richness, because honestly, one really good informative demonstration can be worth more than 1,000 mediocre, noisy ones. It's about quality, learnability over just raw quantity here.
Quality over quantity for behavior. Makes sense.
Yeah. Fourth, develop edge-to-cloud fluency. You need to understand the underlying hardware stacks, not just the massive cloud setups, but also the Jetson-scale inference happening right on the edge device. And you need to optimize for both cloud throughput and that often bandwidth-constrained synchronization between the two.
Bridging the cloud and the device.
Yeah. And finally, maybe most importantly, embed ethics in design. Bias and safety, as we discussed, they aren't academic afterthoughts you bolt on later. They have real physical consequences. They must be baked in right at the pipeline level from the start. That means things like continuous bias monitoring in the data streams, developing explainability frameworks for why the robot acted a certain way, and designing robust human-in-the-loop oversight mechanisms to ensure safe and fair operation.
So what does this all mean? It means these large behavior models, they're really heralding a second revolution in AI, aren't they? We're truly shifting from an intelligence that lived only in language and text to one that is embodied, physical, capable of acting in our world. For data engineers, yeah, this is probably daunting, but it's also got to be incredibly exhilarating. Those pipelines of yesterday, the frozen, batch-oriented static systems, they're essentially being melted down and recast into these real-time circulatory systems we talked about. You're no longer just building plumbing for stale databases of text. You're becoming like the cardiovascular architect for robots that can see, feel, touch, and act. The pipelines aren't passive conduits anymore. They're alive, flowing, rhythmic, tightly coupled with the unpredictable pulse of the physical world itself.
The challenge is absolutely immense, no doubt about it. But the opportunity is equally breathtaking. You know, whoever builds these new circulatory systems effectively, they aren't just engineering data anymore. They're building the very infrastructure for the next leap of intelligence itself. And that raises some pretty fundamental questions, doesn't it? About the nature of intelligence, how it arises, and, well, our role in shaping its future. Thank you for joining us on this deep dive into what feels like the very edge of data engineering.
Indeed. It's a field that's moving incredibly fast, maybe faster than ever. We hope this has given you plenty to think about, plenty to chew on. Until next time, keep exploring, keep questioning, and keep diving deep.